Next we'll be discussing about the architectural principles of the router. So within the router, there are two key components: the control plane and the data plane. A router's input ports, output ports, and switching fabric together implement the forwarding function and are almost always implemented basically in hardware. So these forwarding functions are sometimes collectively referred as the router forwarding plane, whereas the router control plane function is mostly implemented in software. So there are different routing algorithms like RIP, Routing Information Protocol, OSPF, Open Shortest Path Fast Protocol, BGP, Border Gateway Protocol. Those are implemented in the control plane, which are basically the software component of these routing architecture. Next is basically a little bit details into the architectural principles of the router, what you have inside the router network. So there are input port function, and if you see, there are basically three layers are embedded, and those three layers are the physical layer, data link layer, and network layer. Physical layer is for bit level reception, and data link layer is for Ethernet or other wireless protocols like ZigBee implementation, and then network layer for decentralized switching. Given datagram destination, this block basically looks up output port using forwarding table information, and it does that in memory. If the datagrams arrive faster into the switch fabric inside the router than the forwarding rate, then there are options of queuing is also available. So next we will discuss about the internet protocol, starting from the datagram format. Then we will move to IPv4 addressing and ICMP, Internet Control Message Protocol, and then IPv6. So the internet addressing and forwarding are the important components of the internet. So there are two versions of IP in use today, the IPv4 and IPv6, and internet network layer has basically three major components. So the first component, you can see, it is the IP protocol. The second major component is the routing component, which help determine the path of a datagram which it should follow from source to destination. And the third component is a service to report any errors in the datagrams and respond to requests for certain network layer information, and that is the Internet Control Message Protocol, ICMP, which is the network layer's error and information reporting protocol. So now look into these IP datagram format, and we call that a network layer packet is basically referred as a datagram. So this is an IPv4 datagram format. The key fields are version number and header length, and that different type of service, and the datagram length, and identifier, flags, and fragmentation, offset, time to leave, then upper layer protocol, header, checksum, source and destination, address, and then the option and the data field, which is the payload. So note that this IP datagram has a total length of 20 bytes header. Of course, assuming no option fields are there. If the datagram carries a TCP segment, then each datagram carries a total 40 bytes of header. And within that 40 bytes, 20 bytes of 20 bytes are of TCP, as we have seen in the transport layer, and the other 20 bytes are for IP. And you know how to calculate these header, because if you look into the rows, so how many rows are there just before this option and payload field, so you can count that there is oh, 1, 2, 3, 4, 5 rows, and each rows is basically 32 bits. So it is basically the 4 bytes. So if you multiply 5 times 4 bytes, you get 20 bytes. So 20 bytes is the header length of IP datagram. So let us look into the IP fragmentation and the reassembly concept. So the maximum amount of data that a link layer frame can carry is called the maximum transmission unit. Now an IP datagram is encapsulated within a link layer frame for transport from one router to the next. The MTU of the link layer protocol has a very hard limit on the length of an IP datagram. Now, this is not a problem of having a hard limit, but the problem is that each of the link can use different link layer protocol like Ethernet, wireless, ZigBee. So there are different types of protocol are available, and each of these protocols can have different maximum transmission units. So let us consider an example. Suppose the router receives an IP datagram from one link, and after checking the forwarding table, you may find the appropriate outgoing link, and if this outgoing link has an MTU, maximum transmission unit, that is smaller than the length of the IP datagram, then what do you do? So what is the solution? So the solution is to split these larger datagram into smaller datagram. Otherwise, how do you fit the oversized IP datagram into the payload field of the link layer frame? So the solution is basically splitting the fragmentation. So to fragment the data into 2 or more smaller IP datagrams and then encapsulate them, each of these smaller IP datagram, in a separate link layer frame. So we see that we can if there is one large datagram, we can, and based on the MTU maximum transmission unit requirement, they can be segmented into 3 smaller datagram, and then they can be sent to the end host systems. And this fragmentation can be done then in any router based on the link layer frame size requirement, but the reassembly of all those fragments are always done at the end system. Okay, so let us consider an example to understand these IP datagram fragmentation concept better. So consider a datagram of 4000 bytes, where 20 bytes is of IP header and the rest of 3980 bytes is of IP payload data. But it must be forwarded to a link with a maximum MTU size as given 1500 bytes. So these imply that 3980 data bytes in the original datagram must be allocated to 3 separate fragments. So all of the fragments will have the same identification number, and there are some offset field. For example, like geo indicates that the data should be inserted at the beginning of the fragment, and which is beginning which can be represented at a byte number 0, and offset 185 indicates that the next MTU data should be inserted beginning at byte number 1480, which is basically 8 times the offset 185. At the destination, the payload of the datagram is passed through the transport layer, after the IP layer has fully reconstructed the original IP datagram. If one or more of the fragments doesn't arrive, the incomplete datagram is discarded and not passed to the transport layer. But as you know, if TCP is being used at the transport layer, then TCP will recover the lost packets by having the source retransmit the data in the original datagram.